Welcome to the Chill Scientist. Let's jump right in. For most of human history, darkness represented the unknown. Long before physics existed as a discipline, people looked at the night sky and wondered what might be hidden beyond the stars. Myths and stories filled that void. Ancient cultures described creation emerging from chaos or emptiness, a reflection of the human attempt to explain why there was something rather than nothing. To early civilizations, the dark sky was both beautiful and frightening, a silent mystery that seemed eternal. The scientific understanding of darkness began to change in the 17th century with Isaac Newton's description of gravity. Newton showed that every mass exerts a force on every other mass, and that this invisible attraction keeps the planets in orbit around the sun. His laws made the universe predictable and measurable. For the first time, the heavens were not ruled by gods or fate, but by mathematics. Yet even within Newton's orderly framework, there were hints of deeper possibilities. In 1783, John Michell, an English clergyman and natural philosopher, proposed an idea that would later seem astonishingly ahead of its time. He calculated that if a star were massive enough, its gravity could become so strong that light itself could not escape. He called such an object a dark star. The logic was simple. Light, according to Newton's own theories, was made of tiny particles. If gravity affects all matter, then sufficiently strong gravity could trap even light. Michel couldn't prove it. No one could. But his reasoning was solid. He even suggested that astronomers might detect such invisible stars by observing how their gravity influenced nearby visible ones. A few years later, the French scientist Pierre-Simon Laplace independently proposed the same idea. Both men were correct in principle, but their work was quickly forgotten. The physics of the 18th century had no way to test such a concept, and the idea of a star so dense that light couldn't escape seemed absurd. Telescopes were focused on things that could be seen, glowing nebulae, comets, and planetary motions, not the invisible. For more than 100 years, Michel's dark stars remained a curiosity, buried in old scientific papers. It wasn't until the early 20th century that the idea found new life. In 1915, Albert Einstein published his general theory of relativity, replacing Newton's force of gravity with the curvature of space-time. According to Einstein, massive objects bend the fabric of space and time, and that curvature guides how other objects move. Planets orbit the sun not because they are being pulled by an invisible force, but because the sun's mass bends space-time around it, creating a kind of cosmic valley that the planets follow. Einstein's equations allowed for extraordinary possibilities. If mass could bend space, then extreme mass could bend it so much that the fabric of space-time would fold in on itself. In 1916, the German physicist Karl Schwarzschild, serving on the front lines during World War I, wrote to Einstein with a solution to those equations. His math described the gravitational field around a perfectly spherical object with enormous density. According to his solution, there existed a boundary, a radius, beyond which nothing, not even light, could escape. Today, we call that boundary the event horizon. Einstein didn't like the result. He believed nature would somehow prevent such an extreme from existing. Many physicists agreed with him. The idea of infinite density, what would later be called a singularity, seemed to break the laws of physics. But Schwarzschild's math was undeniable, and it became the foundation for modern black hole theory. In the 1930s, physicists began to realize that nature might, in fact, produce such objects. Stars much larger than our sun, say more than 3 times its mass, end their lives violently. When they run out of fuel, nuclear fusion ceases, and there's no longer enough internal pressure to counteract gravity. The star collapses under its own weight. For most stars, this collapse stops when they become white dwarfs or neutron stars. But if the star's mass is above a certain threshold, the collapse continues endlessly. the core's gravity overwhelms everything, compressing matter beyond the point where even light can escape. The result is a black hole. The term black hole itself was first used publicly by the physicist John Wheeler in 1967, but by then astronomers already suspected such objects were real. They observed stars moving in odd ways, apparently orbiting invisible companions. In some regions of space, massive amounts of energy were being emitted from a point that had no visible source. The only explanation was something with enormous mass and no light, a black hole feeding on surrounding matter. For centuries, darkness meant ignorance or fear. By the 20th century, it had become a frontier for discovery. Scientists began to realize that the universe wasn't just filled with stars and light, but also with regions where both light and matter vanished. What had once been mythological, the devouring darkness, turned out to be a fundamental part of the cosmos. Black holes are the most extreme expression of gravity. They mark the limits of our understanding, where the known laws of physics collapse. They challenge the idea that space and time are continuous, that cause and effect are predictable, and that information can never be lost. In learning about them, humanity moved from fearing the dark to studying it, and from studying it to realizing that darkness is not absence, it is structure, governed by the same physical laws as everything else, just pushed to their absolute edge. In the late 17th century, Isaac Newton changed how humans understood the universe. Before him, explanations of motion were based largely on philosophy and observation, but Newton introduced a mathematical system that worked. His law of universal gravitation stated that every object in the universe attracts every other object with a force proportional to their masses, and inversely proportional to the square of the distance between them. With this one principle, he explained why apples fall from trees, why the moon orbits the Earth, and why the planets follow predictable paths around the sun. Newton's laws gave humanity a sense that the universe was stable and knowable. Everything could, in theory, be calculated. Gravity was no longer a mysterious tendency, but a measurable effect, and light was understood to behave like tiny particles, corpuscles, that traveled in straight lines at a finite speed. Newton himself estimated that light was extremely fast, but it wasn't until 1676 that astronomer Ole Romer provided the first real measurement using the moons of Jupiter, estimating light's speed at around 220,000 kilometers per second, or about 136,000 miles per second. Later refinements brought that number closer to the modern value of about 300,000 kilometers per second, or roughly 186,000 miles per second. With these tools, scientists began to wonder what would happen if gravity became strong enough to affect even something moving that fast. In 1783, John Michell did the math. Using Newton's framework, he imagined a star far larger than the sun, perhaps 500 times its radius and many times more massive. If such a star existed, he reasoned, its escape velocity, the speed needed to break free of its gravity, could exceed the speed of light. If light could not escape, the star would appear completely dark. He called it a dark star. The calculation was surprisingly accurate in spirit, though it was based on classical physics. Michell even suggested a way to find these invisible objects, look for stars whose visible companions orbit an unseen mass. His idea was almost prophetic. The same method would later be used to identify real black holes more than a century later. A few years after Michell, the French mathematician Pierre-Simon Laplace reached the same conclusion independently. He argued that if light behaves like matter and is influenced by gravity, then there must exist objects whose gravity prevents light from escaping. But Laplace later removed the idea from subsequent editions of his book, likely because it seemed too speculative. In the late 18th century, there was no experimental way to test such a claim, and the very concept of an invisible star seemed unscientific. For most of the 19th century, scientists focused on refining classical mechanics and optics. James Clerk Maxwell unified electricity, magnetism, and light into one theory, describing light as an electromagnetic wave rather than a stream of particles. Once light was understood as a wave, the concept of it being trapped by gravity seemed incompatible with known physics. Waves, after all, weren't thought to have mass. The dark star idea faded into obscurity, a historical curiosity with no evidence to support it. But the question of gravity and light didn't disappear entirely. Astronomers knew that light bends slightly as it passes through dense materials like glass or water, and some speculated that gravity might have a similar effect. If gravity could bend the path of light, even by a tiny amount, it would mean that space itself was not a rigid stage on which events unfolded, but something that could be influenced by matter. That line of thinking set the stage for Albert Einstein's work in the early 20th century. By the early 1900s, observations began to strain Newton's laws. Mercury's orbit, for instance, precessed slightly more than Newtonian gravity could explain. The difference was small, just 43 arcseconds per century. But it couldn't be ignored. Something was missing from the classical model. Einstein's theory of general relativity, published in 1915, provided the missing piece by redefining gravity not as a force, but as the curvature of space-time caused by mass and energy. This new view of the universe transformed Michel's hypothetical dark star into something much more dramatic. According to Einstein's equations, a sufficiently massive and compact object wouldn't just trap light through Newtonian force. It would warp space-time so severely that all paths within a certain region curved inward. Nothing could escape once it crossed that threshold. This wasn't just a stronger gravitational field. It was a region where the very geometry of the universe turned inward on itself. At first, Einstein and most physicists believed such an object couldn't exist in reality. It seemed like a mathematical anomaly, an artifact of the equations, rather than a prediction about nature. But in 1916, the German physicist Karl Schwarzschild derived an exact solution to Einstein's field equations, describing precisely that kind of object. His solution defined a critical radius, now called the Schwarzschild radius, inside which the escape velocity equals the speed of light. For an object the mass of our sun, that radius is only about 3 kilometers, or roughly 1.9 miles. Compress the entire sun into a sphere that small, and it would become a black hole. Schwarzschild's work was groundbreaking, but it was published during World War I, and he died shortly afterward. His results didn't gain much attention until decades later. Still, his equations laid the mathematical foundation for what would become the modern theory of black holes. By the time physicists returned to the problem in the 1930s, they had new tools, an understanding of stellar evolution, nuclear fusion, and the life cycles of stars. They realized that when massive stars die, they can collapse under their own gravity. If the collapsing mass exceeds a certain limit, what's now known as the Tolman-Oppenheimer-Volkoff limit, roughly 2 to 3 solar masses, no known force can stop the collapse. The object continues to shrink until it crosses its own Schwarzschild radius, becoming what we now call a black hole. The idea that gravity could trap light had begun as a speculative thought experiment in the age of Newton. By the early 20th century, it had evolved into one of the most profound implications of relativity. What started as a dark star in Michel's notebook had become a physical reality, predicted by the most successful theory of gravity ever created. After Einstein and Schwarzschild, black holes remained theoretical for several decades. The equations were solid, but most physicists believed nature would somehow avoid such extreme situations. Space and time curving to infinity seemed too pathological to exist in the real universe. Even Einstein himself dismissed the idea, convinced that some unknown mechanism would prevent complete collapse. By the 1930s, the focus of astrophysics had shifted toward understanding how stars lived and died. The discovery of nuclear fusion as the energy source of stars explained how they shine and why they eventually exhaust their fuel. Once fusion stops, a star can no longer counteract the inward pull of gravity. Smaller stars like the Sun end up as white dwarfs, dense Earth-sized remnants supported by the pressure of electrons. More massive stars collapse further, forming neutron stars about 20 kilometers, or roughly 12 miles, across. These objects are so dense that a teaspoon of neutron star material would weigh billions of tons. But theory showed that even neutron stars have a limit. If a collapsing core is more massive than roughly 3 times the Sun's mass, not even neutron pressure can stop gravity. In that case, the collapse continues indefinitely. In 1939, Robert Oppenheimer and Hartland Snyder published a paper describing this process. Using Einstein's equations, they showed that a sufficiently massive star would undergo continuous gravitational collapse, forming what we now recognize as a black hole. The paper was largely ignored at the time. Oppenheimer soon turned to the Manhattan Project, and astronomy lacked the technology to detect such objects anyway. The post-war era brought better telescopes and new detection methods. In the 1950s and 1960s, radio astronomy opened an entirely new window on the universe. Astronomers began to detect compact, extremely bright sources of radio waves that didn't correspond to any visible stars. Some emitted bursts of X-rays. Others were so powerful they outshone entire galaxies. These phenomena didn't fit existing models of stars or galaxies. At the same time, theoretical physics began to revisit Schwarzschild's old solution. In 1958, the physicist David Finkelstein clarified the nature of the event horizon. He described it not as a physical surface, but as a one-way boundary in space-time. Once anything crossed it, no signal, no light, no matter, no information could ever return. Inside, all paths led inevitably toward the singularity, the point of infinite curvature. As more physicists examined Einstein's equations, new types of black holes emerged in theory. In 1963, Roy Kerr found a solution describing a rotating black hole. Unlike the simple spherical Schwarzschild black hole, a Kerr black hole spins, dragging spacetime around with it. This effect, called frame dragging, creates a region outside the event horizon known as the ergosphere, where space itself is forced to rotate. A rotating black hole could, in theory, extract energy from its spin, a concept later formalized in the Penrose process. By the mid-1960s, mounting evidence suggested that such objects might actually exist. Astronomers identified binary systems in which one star orbited an invisible companion that emitted intense X-rays. One of the first and most famous of these, Cygnus X1, was discovered in 1964. Its X-ray output fluctuated rapidly, implying that the emitting region was extremely small, only a few tens of kilometers across. The unseen object's mass, however, was several times that of the Sun. Nothing known could fit that description except a black hole. In 1967, the physicist John Wheeler coined the term black hole during a lecture. Before that, scientists had used cumbersome phrases like gravitationally completely collapsed object. Wheeler's name captured both the nature and mystery of the phenomenon, and it stuck immediately. Around the same time, researchers began to understand that black holes might not be rare cosmic accidents, but central players in the evolution of galaxies. Observations revealed quasars, quasi-stellar radio sources, so luminous that they had to be powered by something extraordinary. The only plausible explanation was matter falling into supermassive black holes, millions or billions of times the Sun's mass, releasing enormous energy as it spiraled inward. By the 1970s, black holes had moved from theoretical curiosities to accepted astrophysical objects. Observations across multiple wavelengths, radio, X-ray, and optical, consistently pointed to compact, invisible sources with gravitational effects that matched predictions. Einstein's reluctant monster had become an essential part of the cosmic landscape. Yet, even as black holes became real in the observational sense, they raised deeper theoretical problems. The most troubling was what happened to information. In classical physics, information about a system, its composition, energy, and structure, is never truly lost. But in a black hole, everything that falls in seems to vanish completely. If a black hole later evaporates, as Stephen Hawking would propose in the 1970s, what happens to that information? That question became one of the central puzzles of modern physics, connecting gravity, thermodynamics, and quantum theory. By the end of the 20th century, astronomers had confirmed dozens of stellar mass black holes and gathered strong evidence for supermassive ones in the centers of galaxies, including our own Milky Way. What began as a speculative idea in the era of Newton and Michel had become one of the pillars of modern astrophysics. The study of black holes was no longer a fringe pursuit. It was the key to understanding how stars die, how galaxies form, and perhaps how the universe itself might evolve. By the late 20th century, black holes had moved from theory to observation, but most of what scientists knew about them still came from mathematics rather than direct evidence. No one could actually see a black hole, because by definition, light could not escape one. The only way to identify them was by their gravitational effects, how they influenced nearby stars or distorted the light coming from background objects. Detecting something invisible required both ingenuity and increasingly sophisticated technology. One of the earliest breakthroughs came from studying binary star systems. In several cases, astronomers found stars orbiting companions that were completely dark. The visible star's motion could be measured precisely, allowing researchers to calculate the mass of its invisible partner. When those calculations produced masses exceeding 3 times that of the Sun, it ruled out neutron stars or white dwarfs as explanations. The only possible object that fit the data was a black hole. Cygnus X1 became the prototype for this kind of discovery. The visible blue supergiant star, HDE 226868, orbited an unseen companion about 15 times the mass of the Sun. The system emitted powerful X-rays, generated as gas from the visible star spiraled toward the black hole, heating up to millions of degrees Kelvin in the process. In the decades that followed, X-ray astronomy continued to uncover more of these systems, confirming that stellar mass black holes were relatively common. But something else was happening on a much larger scale. Astronomers studying galaxies noticed that many had bright, compact centers emitting tremendous amounts of energy. Some of these, known as quasars, shone brighter than entire galaxies, even though the emitting region was no larger than our solar system. The only plausible explanation was that quasars were powered by supermassive black holes, millions or even billions of times the mass of the Sun, feeding on surrounding gas and dust. The idea that nearly every large galaxy might host a supermassive black hole at its center gradually became accepted. Observations of the Milky Way's core supported this conclusion. Using infrared telescopes, astronomers tracked the motions of individual stars near the galactic center. The stars moved in extremely fast, tight orbits around an invisible point no larger than our solar system, but with a mass equivalent to about 4 million suns. That object is now known as Sagittarius A star, the supermassive black hole at the heart of our galaxy. As technology advanced, astronomers gained new ways to study black holes indirectly. The launch of space telescopes such as Chandra and XMM Newton allowed high-resolution observations of X-rays produced in accretion disks. The swirling matter heated as it falls toward the event horizon. Radio telescopes detected powerful jets of charged particles ejected from regions near black holes at nearly the speed of light. Although the exact mechanism behind these jets remains an open question, it is likely related to magnetic fields twisted by the black hole's rotation. By the early 2000s, black holes had become integral to astrophysical models of galaxy formation and evolution. Supermassive black holes were no longer seen as exotic outliers, but as engines shaping the structure of the cosmos. Their immense energy output regulates star formation, influences interstellar gas dynamics, and may determine how galaxies grow over billions of years. Observations suggest a close relationship between the mass of a galaxy's central black hole and the properties of the galaxy itself, particularly the size of its central bulge. This connection implies that galaxies and their central black holes evolved together. Direct imaging remained a challenge. Even the nearest supermassive black holes were too small and too distant to resolve clearly. The angular size of Sagittarius A star, for instance, is roughly equivalent to seeing a baseball on the moon's surface from Earth. To overcome that, scientists combined radio telescopes across the globe to form a virtual Earth-sized observatory, the Event Horizon Telescope. In 2019, this collaboration released the first direct image of a black hole's shadow, the supermassive black hole in the galaxy M87, about 55 million light-years away. The image showed a glowing ring of superheated gas surrounding a dark center, consistent with the predicted shadow of the event horizon. It was a landmark moment, the first visual confirmation of a concept that had existed on paper for more than 200 years. That image didn't just confirm Einstein's equations once again. It also demonstrated how much of modern astrophysics depends on global cooperation and technological precision. Measuring the light delayed by microseconds between telescopes on different continents required synchronization accurate to a fraction of a trillionth of a second. The resulting data confirmed that the geometry of space-time near the black hole matched predictions from general relativity within a few percent. Even as observations improved, theoretical work continued to push boundaries. In 1974, Stephen Hawking proposed that black holes are not entirely black. Quantum effects near the event horizon cause them to emit radiation, a process now known as Hawking radiation. This discovery linked gravity, quantum mechanics, and thermodynamics in an unexpected way, suggesting that black holes could slowly evaporate over time. For a stellar mass black hole, this process would take far longer than the age of the universe. But for microscopic black holes, it could happen much faster. Hawking's insight transformed black holes from passive sinks of matter into dynamic, evolving systems. The study of black holes now spans disciplines from astrophysics to particle physics. They are used as natural laboratories to test the limits of known theories. The extreme conditions near an event horizon cannot be reproduced on Earth, but they provide clues to how gravity and quantum mechanics might eventually be unified. In that sense, black holes have become more than astronomical objects. They are tools for exploring the fundamental structure of reality itself. From Michel's dark stars to Einstein's equations to the first direct image, black holes have gone from speculation to observation to precision science. Each stage of discovery has redefined humanity's understanding of space, time, and matter. What began as an idea about invisible stars has become a central topic in physics, with implications reaching far beyond astronomy. Black holes are no longer the edge of knowledge. They are where knowledge itself is being rewritten. A black hole is defined not by what it is, but by what it does. It is a region of space where gravity is so intense that nothing, not even light, can escape. What separates a black hole from everything else in the universe is the boundary that marks the point of no return, the event horizon. Understanding what happens at and beyond that boundary requires separating the physical reality from the common misconceptions that surround it. In simple terms, a black hole forms when a massive object collapses under its own gravity to a point where its escape velocity exceeds the speed of light, about 300,000 kilometers per second, or roughly 186,000 miles per second. The escape velocity is the speed an object must reach to break free from a gravitational field. For Earth, it's about 11 kilometers per second, or 7 miles per second. For the Sun, it's about 617 kilometers per second, or 383 miles per second. But if you keep packing mass into a smaller and smaller volume, the escape velocity rises until it surpasses the speed of light. At that point, the object becomes a black hole. The event horizon is not a solid surface. It's a spherical boundary in space-time. If you crossed it, you wouldn't hit anything tangible. You would simply find that all possible paths forward lead inward, toward the singularity. Light emitted inside that region is forever trapped, curving back into the hole. From the outside, no signal can ever escape to inform the universe what happens beyond that point. For a non-rotating, uncharged black hole, what physicists call a Schwarzschild black hole, the radius of the event horizon depends only on its mass. The formula is simple. Rs equals 2gm over c squared. Rs equals 2gm over c squared, where g is the gravitational constant, m is the mass of the object, and c is the speed of light. Using that equation, the event horizon of a black hole with the mass of the Sun would be about 3 kilometers, or roughly 1.9 miles in radius. For a black hole with the mass of the Earth, it would be about 9 millimeters across, about the size of a marble. Everything that falls into a black hole is thought to be compressed toward its center, the singularity, a point of theoretically infinite density where the known laws of physics break down. At that point, space-time curvature becomes infinite, and our current theories, relativity and quantum mechanics, can no longer describe what happens. The singularity is not simply a small ball of matter. It's a region where the geometry of the universe ceases to make sense. The space outside the event horizon, however, remains governed by normal physics. There's nothing special or exotic about the region just outside it, aside from the immense gravitational pull. If you were approaching a black hole, the most dramatic effects wouldn't appear suddenly at the horizon. To you, the experience would seem continuous. Time for you would appear normal as you fell inward, but to an observer far away, your fall would appear to slow down more and more, never quite reaching the horizon. This time dilation effect arises from general relativity. The stronger the gravity, the slower time passes relative to distant regions. From the outside, an object falling toward a black hole appears to freeze at the edge and gradually fade as its light becomes increasingly red-shifted, stretched to longer wavelengths by gravity. Inside the event horizon, all directions lead inward. There's no way to stop or reverse course. Even light, which normally follows the straightest possible path in space-time, is bent so sharply that its trajectory loops inward forever. The concept of down ceases to have meaning. Every direction is toward the singularity. The geometry of space-time around a black hole can be visualized using the analogy of a stretched rubber sheet. A massive object, like a planet or a star, creates a shallow depression in the sheet. A black hole, however, forms an infinitely deep well. Once something passes the rim of that well, the event horizon, it cannot come back out. This visualization isn't perfect, but it helps convey the essential idea. Black holes are not objects sitting in space. They are distortions of space itself. When a black hole rotates, as most do, the situation becomes more complex. The rotation drags space-time around with it, an effect known as frame dragging. Near the black hole, this effect becomes so strong that nothing can remain stationary relative to distant space. The region where this occurs, outside the event horizon, is called the ergosphere. Within it, space is being pulled around faster than the speed of light relative to the outside universe, though locally, everything still obeys the laws of physics. The ergosphere allows for energy extraction through mechanisms such as the Penrose process, in which particles entering the region can split, with one escaping and the other falling into the hole, effectively reducing the black hole's rotational energy. The physics of what happens near the event horizon has been tested indirectly through observations of X-ray emissions and gravitational waves. Matter falling toward a black hole forms an accretion disk. a rapidly rotating ring of gas and dust heated by friction to millions of degrees. The inner edge of this disk marks the last stable orbit before matter plunges past the event horizon. Radiation from the disk provides astronomers with valuable clues about the black hole's mass, spin, and surrounding environment. The detection of gravitational waves in 2015 added another layer of evidence. When two black holes merge, they release energy in the form of ripples in space-time, gravitational waves that spread across the universe. The Laser Interferometer. Gravitational Wave Observatory, LIGO, detected these waves directly, confirming both the existence of binary black holes and the predictions of general relativity. The event marked a new era in astronomy, where black holes could be studied not just through light, but through gravity itself. Despite these advances, the singularity remains a mystery. It's where general relativity, which describes large-scale structure, collides with quantum mechanics, which governs the microscopic world. A complete understanding of black holes likely requires a theory of quantum gravity, something that can reconcile these two frameworks. Until then, the singularity remains a mathematical limit, rather than a physical explanation. The study of black holes is not just about extreme objects, it's about testing the boundaries of knowledge. The event horizon marks more than the edge of a star's collapse. It marks the frontier where our understanding of reality stops working. What happens inside that boundary is one of the most important unanswered questions in modern physics. If a person were to approach a black hole, the experience would depend heavily on the black hole's size. For a small, stellar mass black hole, the kind that forms when a massive star collapses, the gravitational gradient near the event horizon would be extreme. That means the difference in gravitational pull between one end of your body and the other would be enormous. Your feet, being closer to the black hole, would be pulled much harder than your head. The result is a process known informally as spaghettification, where tidal forces stretch objects lengthwise and compress them sideways. You would be torn apart long before reaching the event horizon. For a supermassive black hole, such as the one at the center of our galaxy, the story changes. Because the event horizon is much farther from the singularity, the gravitational gradient there is weaker. In that case, you could cross the event horizon without feeling anything unusual at first. There would be no wall or shock, no visible boundary. You would continue to fall freely, experiencing weightlessness, while time and space behave normally from your perspective. To a distant observer, however, the scene would look entirely different. As you approach the event horizon, your motion would appear to slow down, eventually freezing in place. The light from you would become increasingly redshifted, its wavelength stretched by the black hole's gravity until it faded from view. You would never seem to cross the event horizon at all. From their perspective, you would simply dim and disappear. This difference between what you experience and what an outside observer sees is one of the most striking consequences of general relativity. Time itself flows differently depending on the strength of gravity. Near a black hole, time slows dramatically compared to regions far away. For you, only seconds might pass, while, from the viewpoint of someone outside, millions of years could go by. This isn't an illusion, it's a measurable physical effect. If you could somehow survive crossing the event horizon, something no known material could endure, you would find yourself unable to stop moving inward. The curvature of space-time is such that every possible direction leads toward the singularity. There are no stable orbits, no way to hover or turn around. Even light emitted upward would be dragged back down. You would be following what physicists call a geodesic, the natural path through curved space-time. As you fell, the tidal forces would increase. The closer you got to the singularity, the stronger the difference in gravitational pull between different parts of your body. For a supermassive black hole, these forces might remain tolerable for a while, but eventually they would become overwhelming. Matter itself would be stretched into long streams of subatomic particles. The concept of you would lose meaning long before reaching the singularity. The singularity itself, according to classical general relativity, is a point where density becomes infinite and the laws of physics cease to function. However, it's likely that reality is more complicated. Quantum mechanics suggests that the singularity might be replaced by a region where quantum gravitational effects dominate. In such a scenario, space and time could become discrete, with limits to how small or dense anything can be. Because we don't yet have a complete theory of quantum gravity, what happens at that scale remains unknown. Some theoretical models propose that the singularity might not be a point at all, but a ring, or a region where space-time curves back on itself. In the case of a rotating or Kerr black hole, the equations of relativity even allow for the possibility of passing through the center and emerging elsewhere, a concept known as a wormhole. However, these solutions are purely mathematical and almost certainly unstable in the real universe. Any small disturbance, such as the presence of matter or radiation, would collapse the passage instantly. Even if it were possible to cross into another region of space-time, the tidal forces and radiation levels near the singularity would destroy any known structure. The idea of using a black hole as a gateway remains in the realm of science fiction, though it continues to inspire serious research into the nature of space-time and topology. While the internal structure of a black hole remains hidden, its influence extends far beyond its event horizon. The region just outside it, the inner accretion disk and surrounding space, is one of the most energetic environments in the universe. As matter falls inward, friction and magnetic fields heat it to temperatures of tens of millions of degrees. This produces intense X-rays and gamma rays that can be detected across vast distances. The energy released by matter falling into a black hole can exceed the efficiency of nuclear fusion by an order of magnitude. In that sense, black holes are not just destructive. They're also powerful engines that shape galaxies and drive cosmic evolution. The behavior of time near a black hole has also been confirmed through observation. In 2018, scientists measured the gravitational redshift of light from a star passing close to Sagittarius A star, the supermassive black hole at the center of the Milky Way. The results matched Einstein's predictions almost perfectly. The star's light was stretched to longer wavelengths as it climbed out of the black hole's gravitational field, a direct demonstration of time dilation in action. The paradox of black holes is that they combine two extremes, simplicity and mystery. From the outside, a black hole can be fully described by only three measurable properties: mass, charge, and spin. Everything else about the matter that formed it is lost to the universe. Yet the physics that govern what happens beyond the event horizon remain among the biggest open questions in science. To fall into a black hole, in theory, is to experience the end of everything familiar: space, time, and causality. But it's also to cross into the heart of one of nature's most profound mysteries. What lies beyond the horizon remains hidden not because it's too far away, but because the very structure of the universe prevents the information from returning. Black holes, despite their reputation as cosmic vacuum cleaners, are not objects that simply suck in everything around them. Their gravitational influence follows the same rules as any other massive body. If our sun were magically replaced with a black hole of identical mass, the planets would continue orbiting as before. Earth wouldn't spiral inward. The main difference would be the absence of sunlight and the immediate end of life. The real drama happens when matter gets close enough to a black hole to be captured by its gravity. Gas, dust, or even entire stars can be drawn toward it, forming what's known as an accretion disk. The material in this disk doesn't fall straight in. Instead, it spirals inward, like water going down a drain, while colliding and compressing with incredible force. These collisions heat the matter to extreme temperatures, millions of degrees Kelvin, emitting X-rays and gamma rays before it disappears past the event horizon. The inner edge of an accretion disk lies just outside the point where stable orbits are no longer possible. For a non-rotating black hole, This last stable orbit is about 3 times the Schwarzschild radius. Beyond that, the gravitational pull is so strong that no circular path can hold. In a rotating black hole, however, the situation changes. The faster it spins, the closer matter can orbit before plunging in. This makes rotating black holes more efficient at converting gravitational energy into radiation. Some of them can release up to 40% of the rest mass energy of the infalling matter, a staggering figure when compared to the 0.7% efficiency of nuclear fusion in stars. This energy doesn't only appear as heat and light. Black holes also produce enormous jets of charged particles that shoot out from their poles at nearly the speed of light. These jets can extend for thousands, even millions of light years into space. They are often observed in galaxies with active nuclei, so-called active galactic nuclei, or AGN, and are among the most powerful phenomena in the universe. The mechanism behind these jets is still not fully understood, but magnetic fields are the likely key. As matter in the accretion disk rotates, it twists and amplifies magnetic field lines. These fields channel some of the infalling material and energy away from the disk along the black hole's rotational axis, launching it outward as a narrow, focused jet. Even though the matter near the black hole is falling inward, magnetic forces can redirect a small fraction of it outward with immense speed. These jets have profound effects on their surroundings. They can heat interstellar gas, regulate star formation, and influence the growth of galaxies. In large galaxy clusters, jets from supermassive black holes carve out giant cavities in the hot gas between galaxies, preventing that gas from cooling and collapsing into new stars. Without these jets, galaxies might form stars too rapidly and exhaust their gas early. Paradoxically, black holes help sustain the long-term evolution of galaxies by throttling it. The central black hole of a galaxy and the galaxy itself appear to evolve together. Observations show a tight correlation between the mass of a galaxy's central black hole and the mass of its stellar bulge. The more massive the bulge, the more massive the black hole. This relationship, known as the M-sigma relation, suggests a feedback loop. As the black hole grows by accreting matter, it releases energy and outflows that influence star formation in the surrounding galaxy, which in turn affects how much material is available to feed the black hole. The most extreme examples of this process are quasars, galactic nuclei so luminous that they can outshine their entire host galaxies. Quasars are powered by supermassive black holes, consuming vast amounts of gas at high rates. The radiation from the accretion disk and the jets can be seen across billions of light years, making quasars visible from the early universe. Some quasars formed when the universe was less than 1 billion years old, meaning that their black holes grew to billions of solar masses in a very short time. How they did this remains one of the open questions in cosmology. There are a few possibilities. One is that the first black holes formed from the direct collapse of massive gas clouds rather than from the deaths of stars, allowing them to start larger. Another is that early conditions in the universe, dense gas, abundant matter, and high collision rates, allowed black holes to merge and accrete more efficiently than they do today. Regardless of how they formed, supermassive black holes are now seen as key players in shaping the universe. Their growth and behavior affect everything from the distribution of galaxies to the intergalactic medium. When galaxies collide, their central black holes often merge as well, releasing bursts of gravitational waves that ripple across space. These mergers can kick black holes out of their host galaxies entirely if the gravitational wave emission is asymmetric, sending them drifting through intergalactic space. Supermassive black holes also serve as cosmic anchors. The centers of galaxies are stable because of them. Stars orbit these invisible giants in complex, chaotic patterns, but without them, the structure of galaxies would be different. Sagittarius. A star, the black hole at the center of our Milky Way, is relatively quiet now, but it may have been active in the past. Evidence from X-ray echoes in surrounding gas clouds suggests that it flared brightly a few hundred years ago, perhaps after swallowing a passing star or a gas cloud. When viewed at large scales, black holes are both destroyers and creators. They consume matter, but the energy released in that process seeds the formation of new stars and regulates galactic ecosystems. They are nature's most efficient energy engines, converting gravitational collapse into radiation, heat, and motion on a cosmic scale. Far from being rare or exotic, black holes are now understood to be common features of the universe. Every large galaxy appears to contain one, and smaller ones form constantly from dying stars. The universe is filled with them, silent, invisible, yet shaping the cosmos through their gravity and energy. The idea that black holes could emit anything at all seemed impossible for most of the 20th century. By definition, a black hole's event horizon was the ultimate one-way boundary. Light and matter could enter, but nothing could ever leave. That absolute finality gave black holes their name and their mystery. But in 1974, Stephen Hawking changed that picture forever with a discovery that merged general relativity, quantum mechanics, and thermodynamics into one of the most profound ideas in modern physics. Hawking realized that the vacuum of space is not truly empty. According to quantum field theory, even a perfect vacuum constantly fluctuates with pairs of virtual particles that appear and annihilate almost instantly. Normally, these pairs vanish before they can be observed. However, near the event horizon of a black hole, the intense gravitational field can separate them before they annihilate. One particle falls into the black hole while the other escapes into space. To an outside observer, it looks as though the black hole is emitting radiation. This process, now called Hawking radiation, means that black holes are not completely black. They glow faintly, radiating energy as if they had a temperature. The smaller the black hole, the hotter it is. A supermassive black hole emits radiation so weak that it's undetectable by any current instrument, with an effective temperature only a few billionths of a degree above absolute zero. A tiny black hole, however, would radiate much more strongly, potentially glowing with gamma rays before evaporating entirely. The idea was revolutionary because it implied that black holes could lose mass over time. As they emit radiation, they slowly shrink. For stellar mass black holes, this process is negligible. The evaporation time is vastly longer than the age of the universe. But for hypothetical microscopic black holes, it could happen rapidly. A black hole with the mass of a mountain, for example, would evaporate in a fraction of a second, releasing an enormous burst of energy equivalent to billions of nuclear bombs. Hawking's discovery also tied black holes to the laws of thermodynamics in a deep way. Decades earlier, physicists like Jacob Bekenstein had proposed that black holes must have entropy, a measure of disorder or information content. He reasoned that when something falls into a black hole, its information disappears from the observable universe, but the total entropy of the universe should still increase. To preserve the second law of thermodynamics, black holes must have their own entropy, proportional to the area of their event horizon. Hawking's work confirmed this idea mathematically. The temperature and entropy of a black hole obey the same relationships as ordinary thermodynamic systems, except the quantities are expressed in terms of gravity and space-time geometry. A black hole's entropy is proportional to the area of its event horizon, not its volume. A curious and profound result that suggests information in the universe might be encoded on surfaces rather than in three-dimensional spaces. This concept later evolved into the holographic principle, a cornerstone of modern theoretical physics. But Hawking's discovery also created one of the greatest paradoxes in science, the black hole information paradox. In quantum mechanics, information about a physical system is never truly destroyed. If you know a system's initial state and the laws of physics, you can, at least in principle, reconstruct its past and future. but Hawking radiation appears to carry no information about what fell into the black hole. It's purely thermal, random radiation. If the black hole eventually evaporates completely, the information about everything it consumed seems to vanish forever. That violates one of the most fundamental principles of quantum theory, unitarity, the idea that quantum evolution preserves information. Physicists have spent decades trying to resolve this contradiction. Some argue that the information is somehow encoded in the Hawking radiation itself, though in a highly scrambled form. Others suggest that the information remains trapped at the event horizon in a thin layer of quantum degrees of freedom, sometimes referred to as the black hole membrane or firewall. Still others propose that space-time is more deeply connected than we think, and that information could escape through subtle quantum entanglement effects. None of these solutions have been proven, but all of them point toward a deeper truth, that the intersection of gravity, thermodynamics, and quantum mechanics is the key to understanding the universe at its most fundamental level. Black holes sit precisely at that intersection. The paradox also led to one of the most intriguing developments in theoretical physics, the holographic principle. In the 1990s, physicist Gerard T. Hooft and later Leonard Susskind proposed that all the information contained within a region of space can be described by data encoded on its boundary surface, just as a hologram encodes a three-dimensional image on a two-dimensional film. In this view, the universe itself might be holographic, with the three-dimensional world we experience emerging from two-dimensional information stored on the edges of space-time. In black hole physics, this principle finds a concrete form. The entropy of a black hole scales with the area of its event horizon, not its volume, implying that the contents of the black hole are somehow represented on its surface. This realization has deep implications for cosmology, quantum gravity, and the nature of information itself. It suggests that space and time may not be fundamental quantities, but emergent properties of something deeper, possibly quantum entanglement. While these ideas remain theoretical, they've reshaped how physicists think about the universe. Black holes are no longer just endpoints of stars. They are laboratories for testing the most extreme interactions between gravity and quantum mechanics. Each insight gained from studying them ripples outward, changing how we understand not just the cosmos, but the fabric of reality itself. Even the concept of an event horizon may not be as absolute as once thought. Some models propose that quantum effects could replace the sharp boundary with a fuzzy region where information can leak out slowly. Others speculate that black holes might leave behind stable remnants after evaporation, preserving information in a new form. Whatever the final answer turns out to be, the debate over the information paradox has driven enormous progress in theoretical physics. It has led to new approaches to quantum gravity, including string theory and loop quantum gravity, and to new insights about how space and time emerge from fundamental quantum states. In essence, black holes have evolved from being the universe's most mysterious objects to its most revealing ones. What began as an idea about inescapable gravity now stands at the center of the quest to unify the laws of physics. If black holes can evaporate through Hawking radiation, then in principle they could exist at any size, even microscopic. In practice, most black holes form when stars collapse, and those are enormous by comparison. But the equations of general relativity don't impose a lower limit on mass. In the earliest moments after the Big Bang, the universe was so dense and chaotic that tiny fluctuations in density could have created what are called primordial black holes, miniature versions ranging from subatomic scales to the mass of a mountain. A primordial black hole the mass of Mount Everest would be about the size of a proton, roughly 10 to the negative 15 meters across. One that massed as much as a large asteroid might be no bigger than a grain of sand. Because smaller black holes radiate faster, most primordial ones would have already evaporated completely if they existed. But the largest of them, Those with masses above about 1,120 kilograms, a trillion metric tons, might still survive today, slowly leaking energy into space. These ancient remnants could, in theory, make up part of the universe's dark matter, the invisible mass that outweighs normal matter by a factor of about 5 to 1. Astronomers have searched for signs of them, such as brief flashes of gamma rays that would occur when small black holes evaporate, or gravitational lensing effects caused by their gravity bending light from distant stars. So far, no convincing evidence has been found, but the idea remains plausible, and experiments continue to probe the possibility. On an even smaller scale, particle physicists have wondered whether microscopic black holes could be created in high-energy collisions. For example, inside particle accelerators like the Large Hadron Collider, LHC. If space has extra dimensions beyond the familiar 3 of length, width, and height, gravity could be stronger at very small scales than expected. In such a scenario, when two particles collide at extremely high energy, the energy density could be sufficient to briefly create a tiny black hole. These black holes, if they formed, would evaporate almost instantly, releasing a burst of particles in a characteristic pattern. Detecting such a signature would be revolutionary. It would confirm the existence of extra dimensions and offer direct evidence of quantum gravity. Effects, despite years of searches, the LHC has not found any indication of these microscopic black holes, placing tight limits on the energy scale at which they could exist. But the concept remains one of the most intriguing intersections of cosmology and particle physics. In the early universe, the conditions for black hole formation were far more favorable than they are today. Temperatures exceeded trillions of degrees, and densities were immense. Regions with even slightly higher density than average could collapse under their own gravity before the expanding universe could disperse them. These primordial black holes might have influenced the formation of galaxies by seeding regions where matter could collect. If primordial black holes did exist, they might provide clues about the earliest epochs of cosmic history, times far before the formation of atoms or stars. Their distribution, mass range, and abundance would reveal how fluctuations behaved in the first fraction of a second after the Big Bang, when quantum effects dominated. In that sense, finding or ruling out primordial black holes is as much about understanding the origins of the universe as it is about black holes themselves. Modern cosmology connects this with another question. Could black holes form in the far future through mechanisms other than stellar collapse? Theoretically, yes. If enough matter accumulates in one place, even cold, dark matter particles, a black hole can form. On long enough timescales, over trillions of years, gravitational interactions could cause stars and remnants in galaxies to drift together, eventually forming supermassive black holes or merging existing ones into larger structures. In the very distant future, when stars have burned out and galaxies have stopped forming, black holes will dominate the universe. Over unimaginable spans of time, they too will slowly evaporate through Hawking radiation. The smaller ones will go first, vanishing in bursts of energy. The supermassive ones will fade last, leaving behind a cold, dark cosmos filled with nothing but low-energy photons and elementary particles. This scenario, sometimes called the black hole era, is part of the predicted heat death of the universe, the ultimate thermodynamic equilibrium where all usable energy is gone and nothing new can happen. Black holes are, in a sense, both the beginning and the end of time as we know it. They may have formed in the earliest instance of the cosmos, and they may outlive everything else. From the quantum foam of the Big Bang to the cold silence of the far future, they trace the universe's story from birth to decay. Even the study of black holes themselves might offer clues about how to bridge that vast arc. If we can understand what happens when gravity and quantum mechanics meet at a black hole's singularity, we might finally learn how the universe itself began, and whether beginning is even a meaningful word in a space-time that can curve in on itself. The discovery of gravitational waves transformed black holes from theoretical objects into dynamic, observable actors in the universe. For a century, gravitational waves had existed only in Einstein's equations, ripples in space-time created by accelerating masses. Einstein himself doubted they could ever be detected because even violent cosmic events would produce waves unimaginably faint by the time they reached Earth. But in 2015, scientists proved him wrong. At two facilities known as LIGO, one in Hanford, Washington, and the other in Livingston, Louisiana, researchers had built laser interferometers capable of measuring distortions in space smaller than 1,000th of the diameter of a proton. On September 14, 2015, they detected a tiny transient signal lasting a fraction of a second. It matched precisely the predicted pattern of two black holes spiraling together and merging. The masses were 36 and 29 times that of the Sun, and in the final moments of their collision, they released the equivalent of 3 solar masses of energy in gravitational waves in less than half a second. That single event, named GW150914, was one of the most important discoveries in modern physics. It confirmed the existence of binary black holes, proved that gravitational waves are real, and opened an entirely new way of observing the universe. Instead of detecting light, radio waves, or X-rays, scientists could now listen to the vibrations of space-time itself. Since then, dozens of similar mergers have been recorded, involving black holes of different masses and spins. Each event carries unique information about the systems that produce them. The chirp of a gravitational wave, the rising frequency and amplitude as the two black holes spiral closer, encodes details about their masses, spins, and the distance to the merger. By comparing observed signals with theoretical models, physicists can reconstruct the event with astonishing accuracy. The detection of gravitational waves also revealed surprises. Some of the merging black holes were more massive than expected, suggesting that they might have formed through the mergers of earlier generations of black holes, or through unusual processes in dense star clusters. Others showed signs of high spin, indicating that they may have originated in regions with chaotic dynamics rather than from isolated binary stars. One of the most fascinating aspects of these detections is that they confirm general relativity under conditions far beyond anything we can reproduce on Earth. The final milliseconds of a black hole merger involve gravitational fields so strong and space-time curvatures so extreme that even tiny deviations from Einstein's equations would be detectable. Yet every signal so far has matched his predictions with remarkable precision. The theory remains unbroken, even at the edge of physics. But gravitational waves are not limited to stellar mass black holes. They can also come from the mergers of supermassive black holes, giants millions or billions of times the Sun's mass that lurk in galactic centers. When galaxies collide, their central black holes eventually sink toward each other, orbiting for millions of years before merging. The waves from such events have frequencies too low for LIGO to detect, but they should leave a background hum rippling through the cosmos. In 2023, astronomers using pulsar timing arrays, networks of precisely measured spinning neutron stars, announced evidence of that low-frequency gravitational wave background. The timing variations of these pulsars across the sky showed subtle correlations consistent with the collective signal of countless supermassive black hole mergers throughout the universe's history. It was the first glimpse of the gravitational soundscape of cosmic evolution. This expanding field, often called multi-messenger astronomy, combines gravitational wave detections with traditional electromagnetic observations. In 2017, LIGO and its European counterpart Virgo detected the merger of two neutron stars, an event accompanied by a burst of gamma rays and visible light. While that particular event didn't involve black holes, it demonstrated what could happen when gravitational and electromagnetic signals are observed together. a complete picture of cosmic cataclysms, from the collision itself to the aftermath. Future observatories like LISA, the Laser Interferometer Space Antenna, scheduled for launch in the 2030s, will extend this capability to much lower frequencies. LISA will consist of 3 spacecraft separated by millions of kilometers, orbiting the Sun and connected by laser beams. It will be able to detect mergers of supermassive black holes, the in-spiral of smaller ones into larger ones, and possibly even gravitational waves from the early universe itself. The implications go beyond astrophysics. Gravitational waves provide direct evidence of how space-time behaves when violently disturbed. They allow scientists to test whether gravity travels at the speed of light, whether black holes truly have no hair, meaning no distinguishing features other than mass, spin, and charge, and whether exotic objects like wormholes or gravastars could exist. Each new detection adds another data point to the cosmic record, building a census of black holes and revealing how they shape the universe over time. They merge, grow, and occasionally recoil, kicked across space by asymmetric bursts of gravitational energy. Some may even be ejected from their host galaxies, becoming intergalactic wanderers invisible except for the faint gravitational fingerprints they leave behind. Through gravitational waves, the universe has gained a new voice. Black holes, once thought silent, now speak in frequencies that instruments can record and humans can translate into sound, faint but unmistakable echoes of space-time itself, flexing under unimaginable force. Black holes are not just destructive voids, they're among the most powerful engines of creation in the universe. While they devour matter and light within their event horizons, their influence extends far beyond what they consume. In fact, the energy released near black holes often helps shape galaxies, form stars, and even regulate the growth of cosmic structures. At the center of nearly every large galaxy lies a supermassive black hole, ranging from millions to billions of times the mass of the Sun. The Milky Way's central black hole, known as Sagittarius A star, has a mass of about 4 million suns. It's relatively quiet right now, surrounded by hot gas and a few orbiting stars. But in other galaxies, similar black holes blaze with unimaginable brightness, outshining the combined light of all their stars. These are known as active galactic nuclei, AGN, and when they are especially luminous, we call them quasars. A quasar forms when gas, dust, and sometimes entire stars fall toward a supermassive black hole and form an accretion disk, a rapidly rotating ring of material heated to extreme temperatures by friction and gravitational forces. The inner regions of that disk can reach tens of millions of degrees Kelvin, tens of millions of degrees Fahrenheit, producing intense radiation from radio waves to X-rays. A fraction of that energy escapes along the black hole's rotational axis in the form of powerful jets of plasma that shoot out at nearly the speed of light. These jets can extend for thousands or even millions of light years, punching through the surrounding gas of their host galaxies and beyond. Observations show that these outflows inject enormous amounts of energy into their environments, preventing gas from cooling and collapsing into new stars. Paradoxically, black holes can both trigger and suppress star formation, a cosmic feedback loop that regulates galactic growth. Without this feedback, galaxies might grow too quickly, converting all their gas into stars in a short time. Instead, the energy released by black holes acts like a thermostat for the universe, maintaining a balance between collapse and expansion. In galaxy clusters, the largest known structures in the cosmos, supermassive black holes at the centers of the dominant galaxies, release jets so powerful they carve out cavities in the surrounding hot gas, visible in X-ray images as enormous bubbles. Those cavities prevent the gas from cooling too fast, thereby stabilizing the cluster over billions of years. This regulation has been confirmed through both observation and simulation. When astrophysicists model galaxy formation without black hole feedback, galaxies grow too large, too bright, and too compact compared to what we actually see. Only when black holes are included, injecting energy, stirring gas, and quenching star formation, do the models reproduce realistic galaxies. Even more remarkably, the masses of supermassive black holes are tightly correlated with the properties of their host galaxies. Observations show that the mass of a galaxy's central black hole is roughly proportional to the mass of the galaxy's bulge and the speed of stars orbiting within it. This correlation, known as the M-sigma relation, suggests that galaxies and their black holes grow together, influencing one another throughout cosmic history. This co-evolution raises a question: which came first, the black hole or the galaxy? The answer is still debated. Some theories propose that the first stars in the early universe collapsed into black holes that then grew rapidly, pulling in surrounding gas and helping seed galaxies. Others suggest that galaxies formed first, and their central regions naturally funneled matter inward to form black holes. It's likely a combination of both, a process that varied depending on environment and time. One of the most dramatic examples of black holes shaping galaxies can be seen in radio galaxies like M87, whose central black hole was the first ever directly imaged by the Event Horizon Telescope in 2019. M87's jet extends more than 5,000 light-years, releasing more energy than an entire galaxy's worth of stars. At its core, the black hole's accretion disk twists magnetic fields into a tightly wound spiral, launching the jet outward with astonishing efficiency. What we see from Earth is a steady, powerful stream of matter and energy sculpting its galactic environment on vast scales. The effects of black holes are not limited to the visible universe. They also shape the cosmic web, the vast structure of filaments and voids that make up the universe on its largest scales. Simulations show that feedback from quasars and AGN helps regulate how gas flows through this web, determining where galaxies form and how clusters evolve. The energy released by black holes during their active phases permeates intergalactic space, heating and ionizing gas across millions of light years. In this sense, black holes act as cosmic architects. Their gravity sculpts the local environment, while their radiation and outflows influence the universe on much larger scales. Without them, the distribution of matter, the appearance of galaxies, and even the chemical composition of stars would be different. The paradox is striking. The darkest objects in the cosmos are among the brightest forces of creation. They drive the evolution of galaxies, determine how stars form, and shape the visible universe, all while remaining invisible themselves. The interplay between black holes and galaxies is one of the most beautiful examples of balance in nature. Destruction and creation, collapse and expansion, chaos and order, all woven together by gravity and time. Observing black holes directly is one of the most difficult challenges in astronomy, because by definition, they emit no light. Everything that crosses the event horizon is lost from view forever. Yet scientists have found ways to detect their presence and even create detailed images of their surroundings using indirect methods, by watching what happens to the matter and light near them. For decades, astronomers identified black holes primarily through their gravitational effects on nearby objects. In binary systems where a normal star orbits an invisible companion, the unseen object's mass and the behavior of gas pulled from the star can reveal the presence of a black hole. One of the earliest and best-known examples is Cygnus X1, discovered in the 1960s. It's located about 6,000 light-years away and emits strong X-rays. Detailed measurements showed that its unseen companion has a mass of about 15 times that of the Sun, too massive to be a neutron star. The only explanation consistent with the data was that it was a black hole. These systems, known as X-ray binaries, occur when matter from a companion star spirals toward the black hole, forming an accretion disk that heats up to millions of degrees. The intense X-ray emission from this process can be observed with space telescopes, allowing astronomers to study how black holes consume matter. The flickering of these X-rays even reveals information about the disk's structure and the black hole's spin, because the inner edge of the disk depends on how rapidly the black hole rotates. In more distant galaxies, astronomers observe the same phenomenon on a much larger scale. When supermassive black holes feed on gas and dust, they produce quasars and active galactic nuclei. The radiation from these systems can vary over time as the accretion flow changes, giving insight into the physics near the event horizon. By analyzing the light from these distant objects, scientists can map the distribution of matter and even estimate the black hole's mass based on how fast gas clouds orbit around it. One of the most dramatic breakthroughs in observing black holes came in 2019, when the Event Horizon Telescope, EHT, collaboration released the first direct image of a black hole's shadow. The target was the supermassive black hole in the galaxy M87, about 55 million light-years away. To capture the image, astronomers used a global network of radio telescopes linked together using a technique called Very Long Baseline Interferometry, VLBI, effectively creating an Earth-sized telescope with resolution fine enough to see details smaller than the orbit of Mercury around the Sun. The resulting image showed a bright ring surrounding a dark central region, the shadow of the black hole. The bright ring is formed by light emitted by hot gas swirling around the event horizon and bent by the black hole's extreme gravity into a circular shape. The dark center isn't the black hole itself, but the region where light cannot escape. The size and shape of the ring match the predictions of Einstein's general relativity almost perfectly, confirming the theory's accuracy in the strongest gravitational fields ever tested. In 2022, the same technique was used to image Sagittarius A star, the supermassive black hole at the center of our own galaxy. Because it's much smaller and changes more rapidly than M87's black hole, capturing a clear image was even harder. The gas near Sagittarius, a star, orbits in minutes rather than days. The final image, though blurrier, revealed the same distinctive ring-like structure, proving that the object at the Milky Way's center is indeed a black hole. Beyond imaging, black holes can also reveal themselves through gravitational lensing, the bending of light caused by their intense gravity. When a black hole passes in front of a distant star or galaxy, it can distort and magnify the background light, sometimes creating multiple images or arcs. Although this effect is rare for individual black holes, it's common on larger scales, where massive galaxies or clusters act as lenses. In principle, gravitational lensing could even be used to detect isolated black holes drifting through space by observing temporary brightening of stars as they pass in front of them. Space-based observatories like Chandra and XMM Newton continue to observe X-ray emissions from black hole accretion disks, while infrared telescopes such as the James Webb Space Telescope are pushing our view even further back in time, searching for the first black holes formed in the early universe. By analyzing faint signals from the most distant galaxies, astronomers hope to understand how the first black holes grew so rapidly, some reaching billions of solar masses when the universe was less than 1 billion years old. As technology improves, future instruments will allow even sharper observations. The next generation of the Event Horizon Telescope aims to capture black holes in motion, producing time-lapse movies of matter orbiting near the event horizon. Planned space missions like the proposed Millimetron and the Chinese-led NGEHT project will extend radio interferometry into space, dramatically increasing resolution and sensitivity. These advances will move us from static images to dynamic understanding, from snapshots of shadows to detailed studies of how space and time behave in the most extreme environments nature allows. Each observation will help refine our understanding of general relativity, quantum physics, and the processes that power the most energetic phenomena in the universe. When matter falls toward a black hole, it doesn't simply vanish in an instant. The process is violent, complex, and full of extremes. To understand what happens, it helps to picture the space around the black hole not as empty vacuum, but as a dynamic, curved environment where gravity dictates every movement. Most black holes don't actively feed all the time. Many sit dormant, waiting for something, a star, a cloud of gas, or a stream of dust, to wander too close. When that happens, the black hole's immense gravity begins to stretch and tear the material apart. This phenomenon, known as a tidal disruption event, can rip a star into a stream of gas that spirals inward, heating up and emitting powerful bursts of light before disappearing beyond the event horizon. If the infalling matter comes in gradually, it forms an accretion disk around the black hole. In this disk, material orbits at high speed, sometimes reaching a significant fraction of the speed of light. The gas particles in the disk collide and compress, generating friction and converting gravitational potential energy into heat. The inner regions of the disk can reach millions of degrees Celsius, hot enough to emit X-rays and gamma rays. Accretion is one of the most efficient energy conversion processes known. A black hole can convert up to 10% of the rest mass of matter into radiation as it accretes. For comparison, nuclear fusion in stars converts only about 0.7%. This is why black holes, though invisible themselves, can be the brightest objects in the universe when actively feeding. The energy produced by accretion also drives powerful outflows and jets. These are not emitted from inside the event horizon, but are launched from regions just outside it, where intense magnetic fields twist and accelerate particles outward along the rotation axis. The exact mechanism remains an active area of research, but the leading explanation is the Blandford-Zinayak process, in which magnetic fields anchored in the accretion disk extract energy from the black hole's spin, channeling it into beams of plasma moving at near light speed. These jets can extend for thousands of light years and influence regions far beyond the host galaxy. Observations show that their composition and energy vary with the black hole's spin and accretion rate. Faster spinning black holes appear to produce more powerful jets, suggesting that rotation plays a key role in determining how energy escapes from the system. Closer to the event horizon, the environment becomes dominated by relativistic effects. Time dilation, predicted by general relativity, means that to an outside observer, infalling matter appears to slow down as it approaches the event horizon. The light it emits becomes increasingly redshifted, stretched to longer and longer wavelengths until it fades away. From our point of view, nothing ever truly crosses the horizon. It just seems to freeze at the edge, fading into darkness. For the matter itself, the experience would be very different. As it approaches the event horizon, the gravitational gradient between the near and far sides of an object grows extreme. If the black hole is small, this difference, called tidal force, becomes so strong that it would stretch the object lengthwise and compress it sideways, a process famously nicknamed spaghettification. Near a stellar mass black hole, an astronaut would be torn apart long before reaching the event horizon. In contrast, for a supermassive black hole, the tidal forces near the event horizon are much weaker because the gradient of gravity over the same distance is smaller. A person falling into one might cross the event horizon without immediate harm, only later being crushed as they approach the singularity deep inside. Of course, no one could survive to report the experience. Once past the event horizon, no information can escape. The singularity is where the known laws of physics break down. In classical general relativity, it represents a point of infinite density and zero volume, a region where space-time curvature becomes infinite and no meaningful description is possible. But this is likely a sign that general relativity is incomplete. At such extreme conditions, quantum effects should become important, and a full theory of quantum gravity would be needed to describe what really happens. One proposal is that the singularity might not be a true point, but a region where space-time becomes quantized, broken into discrete units at the Planck scale, about 10 to the negative 350 meters, or roughly 10 to the negative 34 inches. In this view, the singularity might be replaced by a region where gravity and quantum mechanics merge, possibly resolving the infinite densities predicted by classical theory. For now, that's speculation. What's certain is that once matter passes the event horizon, it can no longer influence the outside universe. Its mass and energy, however, continue to affect the black hole as a whole. According to general relativity, everything that falls in contributes only 3 measurable properties to the black hole: mass, charge, and spin. This leads to the famous no-hair theorem, which states that black holes are simple objects. They have no other distinguishing features or hair. Whether the black hole formed from gas, stars, or exotic matter, it looks the same from the outside as long as these 3 quantities match. That simplicity is part of what makes black holes so fascinating. They act as natural laboratories for testing the limits of physics, where matter, energy, space, and time are pushed to their extremes. Observing how matter behaves as it falls in gives us clues about accretion, magnetic fields, and relativity under conditions no experiment on Earth can replicate. The question of what happens to information that falls into a black hole is one of the deepest and most contentious problems in modern physics. It sits at the crossroads of general relativity, quantum mechanics, and thermodynamics, the 3 great pillars of theoretical physics, and exposes the limits of our current understanding. In classical general relativity, a black hole acts as a perfect one-way trap. Anything that crosses the event horizon is gone forever. The black hole retains only the total mass, charge, and spin of what fell in, but none of the details. A library, a planet, or a person? It doesn't matter. To the universe outside, all that information is erased. That picture was consistent until the 1970s, when Stephen Hawking made a discovery that fundamentally changed our view of black holes. By combining quantum mechanics with the curved space-time of general relativity, he showed that black holes aren't completely black. Instead, they emit a faint thermal radiation, now called Hawking radiation, due to quantum effects near the event horizon. The idea is subtle but profound. According to quantum field theory, even empty space is not truly empty. It teems with temporary pairs of particles and antiparticles that pop into existence and quickly annihilate each other. Near a black hole's event horizon, one particle of such a pair can fall into the black hole while the other escapes. To a distant observer, it appears as if the black hole is emitting radiation. This process causes the black hole to lose energy and mass very slowly over time. For stellar mass black holes, the radiation is negligible. Their temperature is only about a 10 millionth of a degree above absolute zero. But for smaller black holes, the effect becomes stronger. In theory, if left long enough, a black hole could evaporate completely, releasing all its mass as radiation over astronomical timescales. Here's where the paradox arises. Hawking's calculation showed that the radiation is purely thermal, random, featureless, and carrying no information about what fell in. If the black hole eventually evaporates, that means all the information about its contents is lost forever. But according to quantum mechanics, information cannot be destroyed. The evolution of a quantum system must always be reversible. Losing information would break one of the most fundamental laws of physics. This apparent contradiction became known as the black hole information paradox. For decades, physicists have debated how to resolve it, and several competing ideas have emerged. One possibility is that information is somehow encoded in the Hawking radiation itself, that the radiation is not perfectly random, but subtly correlated in ways Hawking's original calculation didn't capture. If true, it would mean information slowly leaks out as the black hole evaporates, preserving quantum unitarity. Another idea suggests that information is stored on the event horizon in a kind of holographic form. This concept, known as the holographic principle, arose from work by Gerard T. Hooft and Leonard Susskind in the 1990s. It proposes that all the information about the three-dimensional, Contents of a region can be represented on its two-dimensional boundary. In the case of a black hole, the event horizon would act like a cosmic hard drive, encoding everything that falls in as patterns of quantum information on its surface. This idea gained support from string theory and the development of the ADS/CFT correspondence, a mathematical framework showing that a gravitational system in a volume of space can be equivalent to a quantum field theory on its boundary. In that sense, the interior of a black hole might be fully described by quantum states living on its horizon. However, this doesn't completely solve the problem of how information escapes. In 2012, a new twist was introduced by a thought experiment known as the firewall paradox. It argued that if information does leak out in the Hawking radiation, then the smooth spacetime at the event horizon, predicted by general relativity, must instead become a searing wall of high-energy particles. That would mean anything falling into the black hole would be instantly incinerated at the horizon, contradicting the long-standing belief that one could cross it without noticing anything special locally. Most physicists find the idea of a firewall unappealing because it breaks the equivalence principle, a cornerstone of general relativity. Yet the paradox remains unresolved, forcing theorists to question whether our assumptions about space, time, and information are complete. Some more recent proposals suggest that quantum entanglement might provide the answer. In this view, the interior of the black hole and the emitted Hawking radiation are not separate, but part of a single entangled system. As the black hole evaporates, the correlations between interior and exterior particles might ensure that information is preserved globally, even if it appears lost locally. There's also the possibility that what we call a black hole isn't truly a region of no return at all, but something more subtle, a fuzzball or a quantum remnant in which information is stored in microscopic structure rather than lost in a singularity. These ideas are highly speculative, but they share one goal: to reconcile quantum mechanics with gravity and prevent information from disappearing completely. If the paradox is ever resolved, it will likely reshape our understanding of the universe at its most fundamental level. It could lead to a complete theory of quantum gravity, one that unifies the physics of the very large and the very small, bridging the gap between Einstein and quantum mechanics. For now, black holes remain both laboratories and mysteries. They challenge the laws of physics and force us to confront questions about determinism, entropy, and the nature of reality itself. They are not just objects in space, but windows into the limits of knowledge, where the known laws of science collide and something deeper waits to be discovered. The idea that black holes could have thermodynamic properties was once considered absurd. In the 1960s, physicists treated them as purely gravitational objects, completely cold, featureless, and irreversible. Once something fell in, it was gone, and the black hole simply grew. But in the early 1970s, researchers began noticing strange parallels between black holes and the familiar laws of thermodynamics, the branch of physics that deals with heat, energy, and entropy. The first clue came from a series of theorems proved by physicist Stephen Hawking. He showed that, in any classical process, the total surface area of all black hole event horizons in the universe could never decrease. If two black holes merged, the area of the resulting horizon would always be greater than or equal to the sum of the two original areas. This behavior was strikingly similar to the second law of thermodynamics, which states that the total entropy, the measure of disorder or information content of an isolated system, can never decrease. Jacob Bekenstein, a graduate student at the time, took that similarity seriously. He proposed that a black hole actually has entropy and that it's proportional to the surface area of its event horizon, not its volume. The more massive the black hole, the larger its horizon, and therefore, the greater its entropy. This was revolutionary. It implied that black holes weren't perfectly simple. They had an enormous amount of hidden information encoded on their surfaces. At first, Hawking disagreed. In his view, black holes couldn't radiate or change their entropy because nothing escaped them. But when he performed the quantum calculations a few years later, he discovered the opposite. Black holes do emit radiation, as we've already discussed. That meant they had a temperature and could lose mass and energy. The connection between thermodynamics and gravity suddenly became unavoidable. This relationship, now known as the Bekenstein-Hawking entropy, has profound implications. It suggests that the maximum amount of information, or entropy, that can be contained within a given region of space is determined not by the volume of that region, but by the area of its boundary. This insight eventually led to the holographic principle, which proposes that the entire universe might be describable as information encoded on a lower dimensional surface. In a sense, black holes are the ultimate hard drives of the cosmos. A single supermassive black hole could store more information on its surface than all the matter in its galaxy combined. But unlike an ordinary computer, that information is not accessible to the outside world. It's encrypted by gravity itself, woven into the geometry of space-time. Black hole thermodynamics parallels the familiar laws almost perfectly. There are 4 key analogies. 1. The zeroth law states that the surface gravity of a stationary black hole is uniform across its event horizon, just as temperature is constant throughout a system in thermal equilibrium. 2. The first law links changes in mass, area, spin, and charge to energy, entropy, and a temperature, the black hole version of the first law of thermodynamics. 3. The second law asserts that the total area of event horizons cannot decrease, mirroring the second law's statement that entropy never decreases. 4. The third law says it's impossible to reduce a black hole's surface gravity to zero through any physical process, just as it's impossible to reach absolute zero temperature. These parallels are more than mathematical coincidences. They suggest a deep connection between gravity, thermodynamics, and information. Many physicists now believe that space-time itself may be an emergent phenomenon, a kind of statistical average of microscopic degrees of freedom, much like temperature and pressure emerge from the collective behavior of atoms. If that's true, black holes could be the key to understanding what space-time is made of at the most fundamental level. Black hole thermodynamics also bridges the cosmic and the quantum. It connects the geometry of curved space-time with the language of entropy and information, hinting that the universe's most extreme objects obey the same underlying rules as a cup of coffee cooling on a desk. The temperature, the entropy, the flow of energy, these are all aspects of a deeper, unified picture. In this framework, the event horizon is more than just a boundary in space. It's a physical surface with measurable properties, a kind of membrane that obeys the laws of thermodynamics. Some physicists even describe black holes as behaving like fluids, with viscosity, conductivity, and surface tension defined by their gravitational properties. These analogies have become tools for exploring quantum gravity and for modeling how space-time behaves at its limits. The connection between area and entropy, first glimpsed in the 1970s, has since become one of the cornerstones of theoretical physics. It's not just a property of black holes, it seems to apply to the universe itself. The maximum entropy that can fit in any region of space appears to scale with its boundary area, not its volume. That simple but radical observation underpins much of modern cosmology and has reshaped how physicists think about information, gravity, and the nature of reality. The holographic principle emerged from the strange realization that black hole entropy depends on surface area rather than volume. In normal physical systems, like a box of gas or a cup of water, the number of possible microscopic states, or the total entropy, scales with the amount of matter inside, meaning with the volume. But in a black hole, that relationship collapses. Everything that falls inside is somehow encoded on the surface, like information projected onto a two-dimensional sheet. This observation led theorists to propose a radical idea. Perhaps the entire universe works that way. Perhaps the three-dimensional world we experience, all the stars, galaxies, and even space itself, is fundamentally a projection of information encoded on a distant boundary, just as a hologram creates the illusion of depth from a flat surface.